So in section 4.3, we are going to be looking at monotonic functions and the first derivative test. And honestly, this is going to feel very similar to what we did back in section 4.1, where we were looking at local extrema and absolute extrema. So let's go ahead and just take a quick moment and review that. So we'll just go ahead and look at these visually. So we're asked to identify any local and absolute extrema. And let's go ahead and assume that this is a closed interval. So the function's domain is closed from -4 to 4. Because it is a continuous function that's on a closed interval, we are guaranteed absolute extrema. But of course, remember that we'll also have local extrema, and absolute extrema are still local extrema. So let's see what we have right here. We have something happening at x equal to -4. Well, this is the highest point in the graph, so this is going to be a maximum. Indeed, it's an absolute maximum because it is the highest point in the graph. And what is its value? 2. So it's an absolute maximum value of 2 at x equals -4. And indeed, this is also a local maximum as well. And then let's see, do we have any other maximums? Yeah, we have another local maximum of 0, and the other endpoint right here are 2 other local maximum of, let's see, that middle one is of 1 at x equals 0, and there's also a local max of, let's see, that endpoint over there is going to be -1 at x equals 4. So we went ahead and just looked at the local and absolute maximums there. And we could go ahead and do a similar argument for the minimums, where we have a local minimum of -2, or at -2. So we have a local minimum of 0 at x equals -2. And then we also have a absolute and also an absolute and also a local minimum of, and this would be the y value, -3 at x equals 2. So we have a lot of extrema, and we've started to even look at them in terms of the derivative, and that's what we're going to go ahead and use down below. And we're just going to extend the idea a little bit further than what we did before to talk about where is it increasing and where is it decreasing. But the important thing to recall is that what is the derivative at each of these values? Well, the derivative at each of these values, let's say c, is equal to 0. These were basically critical points or endpoints. So that is the important thing to remember. Is extrema occur at critical points or endpoints. The thing that we're going to look at now that we didn't before is what is the graph doing in between these intervals? Well, they're going to either be increasing or they will be decreasing. So up to this point, we've just used essentially observation techniques. So let me pause to see if there's any questions. So let's go ahead and explore the critical point idea a little bit further. And we're going to really focus on how can we figure out when is the function increasing and when is the function decreasing. So of course, we know the derivative as a rate of change. So we're going to have to go ahead and observe what is happening with the derivative in between the critical points. So let's go ahead and find the critical points. And recall, to find the critical points, you first take the derivative. So f prime of x. In this case, we are looking at a cubic function, x cubed minus 12x minus 5. We have 3x squared minus 12. That is our derivative. Now, let's go ahead and set this equal to 0 to find our critical points. So we will have 3x squared minus 12 set equal to 0. Add 12, you get 3x squared equal to 12. Divide by 3. You get x squared is equal to 4. And then we have x is equal to plus or minus 2 by taking the square root. So again, we have the graph over here just to kind of check our answers algebraically as we go. but you can see at -2, we have a local maximum, and at +2, we have a local minimum. So if we want to go ahead and use the calculus or the derivative to understand what is happening in between these critical points, we're going to just go ahead and break up the domain based off of the critical points. So what we're going to do is consider the different parts of the domain. We know the natural domain of this function is all real numbers. So let's consider the domain from -infinity to -2. And then we'll go from -2 to +2, and then we'll go from 2 to infinity. And the reason we want to go ahead and break up the domain, and we'll formalize this in the first derivative test here on the next slide or two, is remember that extrema occur at critical points, but not every critical point is a local extrema. There may be a case where like the graph goes like this, flattens out, and then continues up. So there's no actual maximum. And that's what we're going to be able to look at using the first derivative test. So the reason we broke up the domain is because we want to figure out what is happening in between them. We want to figure out if it's increasing or decreasing. So in order to do that, we're going to take the derivative and we're just going to plug in some value into the derivative that's part of the domain of that particular interval. So let's go ahead and just pick something really easy. Let's go ahead and do f prime of -2. Actually, pause. Remember that this is an open interval, so we can't use -2. -2 would just give us 0. So let's go ahead and use -3. So when we plug in -3, notice we're plugging it into the derivative. We're going to get a value. So if we did this, we would have 3 times -3 squared minus 12, which works out to 15. Notice that this is positive. So if we're looking at 3, we actually have a tangent line that is going to be positive. In other words, we now know the function is increasing on the interval from -infinity to -2. And if you look at this part of the graph, that the slope of the tangent line will always have a positive slope. That is to say, the original function is increasing. So what we'll go ahead and do is pick some other points, and honestly, it's entirely up to you. Anything in this interval, I'm going to do f of 0 here because that's a nice easy one. So f prime of 0, we're plugging it into the derivative. So we have 3 times 0 squared minus 12, which gives us minus 12. So notice that this is negative. So what does that mean about the interval from -2 to 2? It's decreasing. Okay, and then if we did this for the last open interval that we broke the domain up into, let's say f prime of, again, any value in that interval is fine. I'm going to just choose 3 because it's the smallest one that's easy to compute. So you would have 3 times 3 squared minus 12, which would, of course, compute also out to 15 because we have as a fact, it's an odd function. Or well, the original function's odd, the derivative is even. So, well, that is positive. So it's going to be increasing. So we now have answered this question, is we've identified the open intervals for which the function is increasing and for which the function is decreasing. So is this one and this one, they're increasing, and this middle one, they're decreasing. So that's really, again, just kind of using what is the derivative. The last thing we will want to observe is the actual local extrema. Let's go ahead and look at the local extrema. If we think about what is happening when something switches from increasing, so this open interval from -2 to 2 is increasing, but the second interval, the first interval from -infinity to -2 is increasing, this second interval from -2 to 2 is decreasing. So whenever you have this switch where you go from increasing to decreasing, you have an extreme value. In this case, you have a local maximum. And that's going to be at x equals -2. So the local maximum, and what is the value? The actual local max, well, to figure that out, is equal to, the value is equal to f of -2. Plugging that into the original gives you 11. So that's where that came from. So the important thing to grab right here in red is what happens when you switch from increasing to decreasing. Well, you have a local maximum. In the very same thought process, whenever you switch from a decreasing to an increasing, you have a local minimum. Notice that it's not absolute, because we would have to kind of consider like the rest of the domain. But this does give us a good way to find local extreme. So a local minimum and of f of 2, so plugging f of 2 into the original gives you -21, and that's at x equals 2. So we want to go ahead and make sure we understand when you switch from increasing to decreasing, you have a local max, and when you switch from decreasing to increasing, you have a local min. And we're going to summarize that next in the first derivative test. So one way you could even look at this is just by considering we're essentially making a sign chart. This came up as during the question and answer section. We have basically the domain being split up, and then we have these columns right here. And what we're trying to do is in this middle column, or in the middle row, we're trying to figure out if it's positive or negative. In the bottom row, we're then trying to figure out if it is increasing or decreasing. And then in the top row, we're actually just breaking up pieces of the domain. So just to kind of look at what's happening, we're essentially creating a chart. I just didn't put the lines to clutter it. So again, the important thing right here is this transitioning between increasing and decreasing. That is something we've actually already looked at a little bit. If you recall, this chart was in section 4.1. So you can see right here, wherever you have your critical points, and remember critical points also occur where the derivative is undefined. So there's all our critical points. Then you will go ahead and be able to maybe check for extrema there. Well, the important thing to note is, again, a critical point does not necessarily guarantee an extrema, as we can see right here in C1. So to summarize that last little bit, the points of the original function have a minimum value, say lowercase m, if on the left of it, the derivative is negative, where if on the right of it, the derivative is positive. So this is the exact same scenario we just talked about. We went from decreasing, increasing, causing a minimum value. This occurs just at one point here, namely C3. PO would be very happy about it. Star Wars joke, they're terrible. Okay, so let's also consider whenever you had a maximum value, that was when you were increasing or positive on the left and negative on the right, which caused us to go from this positive increasing to negative decreasing, giving us a minimum. You can see that occurred at a couple spots. So we were increasing to decreasing right here at C4. It also occurs right here at C2. So C2 and C4 are the two portions of our original function where it is switching from positive to negative, aka the derivative is positive negative, switching from increasing to decreasing. So that right there is the first derivative test for local extrema. So it's rather intuitive if you just understand that we're looking at when is the derivative positive and when is this negative. So the way the test works, and I'll kind of break down, I'll just kind of highlight the steps right here. The first step was to actually find the critical point. So suppose that C is a critical point of a continuous function and that f is differentiable at every point in some open interval containing C, except for that C itself. So we're going to look at the critical point. Then if we're going to be looking, then we'll just go ahead and do a quick little comparison. This is where we essentially make that sign chart. So if you switch from negative to positive, that is to say you're decreasing to increasing, you have a local min. Positive to negative, well, that's where you have a local max. And there is also the scenario that the sign doesn't change. This is where there's actually no local extrema right here. So number 3 means that the critical point does not necessarily mean a local extrema. And again, I've mentioned that a few times, but just because you have a critical point does not mean it's a local extrema. But if you have a local extrema, that is going to be a critical point. So it's kind of one of those things. Critical point does not imply, so CP does not imply a local extrema, but the other way is true, that if you actually have a local extrema, that is when you do have a critical point. Extrema, and that, of course, does imply a critical point. So what we're going to go ahead and do is just kind of work through the test a few times in a more complicated example, and that will pretty much cover the first derivative test. In section 4.4, we talk about the second derivative test, but let me just pause to see if there's questions. So our first example we're going to do is with this function right here. And you can see the advantage to this is like the quadratics, the cubics, I'm pretty comfortable and I have a good idea of, I know exactly what the graph looks like. And many of you probably do just coming from pre-calculus, and we've been doing a lot of math for the last 12 weeks. But something like this is, even to me, is not right at the forefront of my mind. Like if I didn't have this graph down here, I probably wouldn't have a clue what it looked like. I knew it would probably be smooth because it kind of looks like a polynomial, but you can see right here, this is where calculus will really help us just to identify the extreme values if we don't have the graph. So this problem will walk us through. And my suggestion, whenever you look at a problem, before you even start going through the calculus, if you just think about distributing this right here, it gives you a much nicer function to work with. Remember, this is x to the 1. So if you distribute this, you get x to the 4/3 minus 4x to the 1/3. So if I just take that moment and distribute, I don't have to even worry about product rule. I'm just going to use the chain, not even chain rule. I'm going to just use the power rule. So let's go through these steps. So part A asks us to find the critical points. To find the critical points, we take the derivative. So f prime of x, in this case, is going to be 4/3 comes down, and we have x to the 1/3, because we subtracted 1 from the power, minus 4 times 1/3 x to the negative 2/3. All right, so there's a couple things that we can go ahead and look at right here. Let me take a quick look. I'm trying to remember how my math lab does a few of these things. Now, there's a couple approaches here. So the first thing I'm going to do is I'm going to get rid of the negative exponent. So I'm going to rewrite this. I'm going to actually factor out the 4/3, and I'm going to rewrite this as x to the 1/3 minus 1 over x to the 2/3. So again, I'm factoring out the 4/3 to clean it up because I really want to focus on what's happening in here. So when we go to set this equal to 0 to find the critical points, there's a couple ways to approach this. I'm going to actually go ahead and get a common denominator, because it's really nice if you have a fraction, like you have a function where there's like a function on the top and a function in the denominator, you just set each of them equal to 0 separately, because again, the top will be where you have the critical points, where the function's equal to 0, so you have your tangent lines. The denominator is where you would have something like a cusp or a corner, because that's where the derivative would be undefined. So what I'm going to go ahead and do is I'm going to multiply the bottom by x to the 2/3. At the same time, I'll multiply the top x to the 2/3. Because when I do this, I have 4/3 out in front, and then I have x minus 1 in the numerator, and I have x to the 2/3 in the denominator. So this right here just makes it a little bit easier for me to go ahead and figure out my critical points because it's purely in terms of the numerator and denominator. So I'll set the numerator equal to 0, and then I'll set the denominator equal to 0, and that's how I'll obtain all my critical points. So x minus 1, set that equal to 0, x equals to 1. That's my critical point where I have some sort of horizontal tangent line. And the other scenario we would look at is, other scenario we'll look at is when we have the denominator x to the 2/3, and we set that equal to 0. And of course, you could think about raising both sides to the 3/2 if you want to do it formally, or you may have just noticed, oh, x is definitely 0 here. So this right here is my these are my two critical points. And we could even observe a little bit what happens even as we go, just to confirm as we're looking at this. So you can see right there, the critical point x equals 1 is going to be an extrema, but this right here is a vertical tangent line. So that's why we have a critical point there, because the derivative is undefined. But notice again, the first derivative test will reveal that this is not necessarily an extrema. So let's actually go through the computations and consider part B, which is essentially just asking us to make that sign chart. So the domain, if you look at this original function, is all real numbers. There's no denominators to worry about. There's no radical. Well, there is a radical in this, but remember, a cubic, you're allowed to plug in both negatives and positives, so that's okay. So our natural domains are real numbers, but what we're going to do is consider the function from -∞ to 0. Again, make sure we order this. 0 comes first. From 0 to 1, and then from 1 to infinity. So that right there is that is my domain broken up into 3 pieces. The second part, I'm going to consider like f prime of some value in that domain. And then once I have that value, I'll be able to tell if it's increasing or decreasing. So of course, remember at this point, because we're trying to figure out if it's increasing or decreasing, we want to plug it into the derivative. So that's another nice part of just simplifying this like so, that this becomes a little bit easier to deal with. So if we do, let's say, f prime of -1, I'm going to even just consider what happens that I have, if I plug -1 in here, I'm going to have a minus, so this will just be a negative over a positive. And notice that the denominator is always going to be positive because of the square. So this is going to just be a negative. I'm going to do f prime of, let's say, 0.5. I know that the denominator is always going to be positive, but if I do 0.5 minus 1, I notice the top is going to be negative, and I'm not necessarily worried about the value. I'm just glancing through and just trying to determine if it's increasing or decreasing, positive or negative. And then f prime of, let's say, 2, well, you have positive over positive. So that means we are decreasing, decreasing again, and then finally increasing on our third interval. And sometimes I'll just put like little arrows under here because that'll remind me like, oh, if I switch from decreasing to increasing, this right here is where I'm starting to answer part C. So part C, which is, at what points, if any, does f assume a local maximum or minimum value? So basically it has a local min at x equal 1. So so again, notice part C is at what point. So it's not asking what the value is, it's just asking what is the location of it. Then part D is where, not B, part D is where it answers that last question, what are the values? And then remember to find the values, you go ahead and plug in that critical point back into the original. So the original, which is way up here, is 1 to the 4/3 minus 4 times 1 to the 1/3, which works out to be 1 minus 4, or -3. So that right there, you can see is consistent with what our graph is down below. And that is how you apply the first derivative test from the beginning to the end. So let's consider another example here. F of x equals to x squared minus 3 times e to the x. So this one, again, you could go ahead and distribute, but you're still going to need the product rule. So I'm going to not mess with that. And it's one of those functions I really don't know off the top of my head a good idea of what it looks like, just because it is a combination or a product of two functions, a quadratic and an exponential. So I'm going to just go ahead and jump right into the calculus and take the derivative. So part A, I'm going to take the derivative first. F prime of x, I'm going to need the product rule. So the first, x squared minus 2, times the derivative of the second, which is e to the x. Plus the second, which is e to the x, times the derivative of the first, which is just going to be 2x minus 0, or 2x. Now, this looks a little bit messy at first, but realize that there's the common e to the x. So I'm going to go ahead and pull that e to the x out. And the first term I'll be left with x squared, and the second term is where the 2x will come from. And then I'll have the minus 2 as well. So I just kind of did a couple algebra steps in my head, but the e to the x was common, so it came out in front. Then we have x squared plus 2x, then minus 2. So again, we are going to now set this equal to 0, but you could do this now or at the next step. I'm going to just do it now. I could factor this as x plus, let's see right here. Oh, there's a little mistake right here. That won't factor nice. Let's back it up, and you may have caught this. This should not have been a 2. This should have been a 3. So this one as written won't factor nice, but when I rewrite this, I think I got ahead of the square. So let's fix that. That should be a 3, which makes this a 3, which makes it much nicer because we could factor this as x plus 3 times x minus 1. Because 3 times -1 gives you -3, and 3 plus -1 gives you +2. So now when you set this equal to 0, you can even see what's happening. We're just taking, all we're doing is setting our derivative equal to 0. So really, you could have even thought about that right from the get-go. So e to the x is equal to 0, x plus 3 is equal to 0, and x minus 1 is equal to 0. Realize that this has no solution. There's no power that you could plug into x and that go away. So that's not a critical point. That's just an extraneous term, which is okay. X is equal to -3 is our first critical point, and x is equal to 1 is our second critical point. So that is the answer to part A. Our critical points are -3 and 1. And just like before, we're going to make a sign chart that breaks up the domain of the original function. So I think you will have a lot of the functions will be -infinity to infinity. Just as we get in the hang of this, you may have some interesting ones at the end of the homework. I can't remember off the top of my head, but if you ever do have trouble, remember to feel free to ask. So let's break up the domain from -infinity to -3 is our first critical point. From -3, I'm going to slide this over, from -3 to 1 is our second interval. And from 1 to infinity is our third interval. And again, I'm also thinking this is -infinity, because if you think about these functions separately, you could plug anything into either of those also. So that's our domain. Let's now consider f prime of some value. So again, you're free to choose pretty much anything you want. A couple things that may help you, just recall that e to the x is always positive. That's useful, just to kind of note that e to the x is greater than 0 for all values of x. So you really could kind of just ignore that term. So if you do like f prime of -4, I'm just thinking about this. We have a positive times a negative, because when you plug -4 into 3, it gives you a negative. Then it's going to be times another negative. So we see that this is going to be positive. So this is giving us even our answer to part C is that it's going to be increasing. So again, we'll just kind of answer C as we go. Oh, we're not quite answering. C is asking for the, never mind, we're not answering C. C is asking for the actual location. So we just know we're increasing right here. C will ask for the actual if there's extrema. So if we do f prime of 0, I'm going to take the opportunity to use 0 whenever I can. So when I plug in 0, let's see what happens. This is positive, and this is negative. So it's positive times negative, which is negative. So we'll be decreasing on this second interval. Then lastly, I'm going to pick, let's say, f prime of 2. So this is going to be, let's see, this is to be positive, this will be positive, and this will also be positive. So it's a positive times a positive times a positive, which is positive. So we are going to be increasing. So now we can see that if we switch from increasing to decreasing, we have a local max at, let's see, x value. This is x equals -3. And then because we go from decreasing to increasing, we have a local min at x equals 1. So that answers part C. Part D, of course, we want the value. So we have to go ahead and just plug it back into the original. So the original is way up there. So the value is actually, let's see, f of -3, which you can verify this one yourself. After it's all said and done, is going to be 6 over e cubed. And then the second one, when you plug in 1, f of 1 is equal to -2e. So you can see right here, we have the local extrema, max and min. And again, we can see they're not absolute extrema in the case, well, this is an absolute min, but this is not an absolute max. The local or the first derivative test is only for local extrema. If we wanted absolute extrema, we would have to consider, like, is this on a closed domain, and things like that. We'll find that in 4.6, when we do optimization, we're typically going to be dealing with some sort of closed domain, just because optimization represent real objects, which are bound by time and space, mostly space. But let me pause and see if there's any questions. And if you are watching this video, just pause regularly and just make sure everything makes sense. So let's go ahead and look at one more example. 4 is pretty similar to what we've been doing already. And the only thing is we don't have a domain that's all real numbers. We're restricting the domain. So you will want to go ahead and kind of think about absolute extrema. But again, this is pretty similar to what we've already done. Number 5 is something similar to what we did earlier in this semester, where we essentially had to find the coefficients for a function, in this case, a quadratic function that satisfies a certain set of criteria. So this is actually a fun little exercise because it makes sure you're understanding what are you plugging into what at each step along the way. So determine the values of the constants a and b. So a and b are the constants, and namely they're the coefficient of the quadratic term and the coefficient of the linear term of this given quadratic function f. And notice that because we have two variables, In order to solve for two variables, you actually need two equations. And those two equations we're going to find from this information that we're given. It doesn't look like a lot of information, but it's actually all we need. The absolute maximum is at the point 1, 2. Well, let's go ahead and extract what does this 1, 2 mean? They literally told us a point on the graph. So what they're literally saying when we're looking at 1, 2 is when you plug in 1 to the function, you set it equal to 2. In other words, let's go ahead and plug 1 in. So we have a times 1 squared plus b, which is in this case 1. Well, excuse me, b is not 1. B is what we're solving for. X is the 1. We set it equal to 2. So we have a plus b is equal to 2. So this is one equation. How do we get the other equation? Well, we're told that it's an absolute maximum. Remember, if you have an extrema, you have a critical point. Extrema implies critical points. So extrema implies a critical point. So let's take the derivative. What's going to happen when you take the derivative is you have f prime of x is equal to 2ax plus b. Remember that a and b are constants, so the 2 comes down in front, gives you 2a, and the derivative of x is just 1. Okay, so what is our critical point? The critical point is the x value. X is equal to 1. So what that's saying is when I plug 1 into the derivative, I'm equal to 0. So f prime of 1 is equal to 0 because 1 is the critical point, the value of x that I plug in that makes my derivative 0. So that is going to give us 2a times 1 plus b equal to 0, or just 2a plus b equal to 0. But notice now we have two equations that we can go ahead and solve by using some system of equations. You may choose to substitute, you may choose to use elimination, but all we have to do at this point is solve this system, namely a plus b equals 2 and 2a plus b is equal to 0. I'm going to just go ahead and subtract the two functions, or the two equations. When I subtract them, we will end up getting minus a is equal to 2, because a minus 2a is minus a, and 2 minus 0 is 2. So we find a is equal to negative 2. And then to find b, you'll just take this negative 2 and plug it back in. So let's say we would then have minus 2 plus b is equal to 2. In other words, b is equal to 4. So we have found the constants that satisfy the given conditions. And honestly, you could even check this by just plugging a and b back in, graphing it, and you'll see that this does have its vertex at the point 1, 2, and it is going to be concaving down because you can see the positive quadratic term. So again, that is the first derivative test. It helps us find local extrema. What we'll also be looking at is the second derivative test, which will help us find, again, local extrema, but it'll also allow us to find something known as inflection points and concavity. So basically when a function switches from increasing to decreasing. And again, that is going to be something that we'll explore more, or not, I should have said, when the derivative switches from increasing to decreasing. But we'll explore that more in section 4.4. Good luck. If you have questions, of course, always feel free to let me know. And finish strong. We only have a few weeks left.